In this presentation, I'll discuss the many applications of Mathematica's numerics functions and give tips on how best to use and combine them. I'll begin with a quick review of Mathematica's main numerics functions, including examples of ways you can use them. Next, I'll show how to control Mathematica's numerical algorithms in detail, and I'll also show a few ways to monitor methods while they're running. Then I'll spend a few minutes talking about the different kinds of approximate and exact numbers that are used by Mathematica. Understanding these is important to get the most out of numerics functions. Finally, I'll give some general tips on programming with Mathematica's numerics functions, including techniques for optimizing performance. Let's begin with a very brief overview of the core Mathematica numerics functions and their applications. The Mathematica function that performs numerical integration, or quadrature, is an integrate. Here we apply it to a function of one variable. If you need to integrate a list of points rather than a function, then you should first interpolate your points. Then you can use an integrate as usual. To compute a path or contour integral, first parameterize the path. Here we parameterize a contour that circles the point z equals 2 in the complex plane. F of z is the function we want to integrate. We can then perform the numerical integration by using the chain rule. This integral corresponds to a complex residue calculation, so we can check our result using the built-in residue function. The Mathematica function that handles ordinary differential equations and partial differential equations is ndsolve. Here's a simple example of solving an initial value problem. The solution in this case is the sinusoid. Here's a much more exciting example of solving the quantum mechanical Schrödinger equation, a partial differential equation. The solution gives the probability of finding a particle at a given position and time. In this case, it's a particle rolling back and forth in a periodic potential well. A useful special application of ndsolve is to obtain a numerical indefinite integral or antiderivative function. In this case, we want to obtain an approximate function that is the integral of sine of x of x. This is equivalent to f satisfying this differential equation, which we can solve with ndsolve. We then have the indefinite integral as an interpolating function. Here's an animation of f together with the integrand sine of x of x. The core function for numerical equation solving is findRoot, which searches for a local numerical solution of one or more equations. Here's a very simple example of solving an equation which can't be solved in closed form. One important application of findRoot is in setting up numerical inverse functions. Given this definition of y of x, how can we find x of y? We can define a new function inverse of t, which, for each value of t, numerically solves the equation y of x equals t. The resulting function can be used like any other function in Mathematica. Each point on this plot involves one call to findRoot. Mathematica has numerical functions for both local and global optimization, including constrained optimization. The function findMinimum searches for a nearby local minimum. The function nMinimize works a lot harder and tries to find the global minimum. Both findMinimum and nMinimize can also perform constrained optimization. In this example, we constrain x and y to points satisfying this predicate. And we find the global minimum on the boundary of the region. Mathematica has many linear algebra functions, but linear solve is probably the most important one. It's the workhorse behind many other numerical algorithms. Here's a simple example of solving 4 linear equations with integer coefficients. And here's a larger example of solving 20 linear equations with random real-valued coefficients. An important special concept related to linear algebra is sparse arrays. These are efficient, specialized representations of matrices and other arrays in which most of the elements are 0 or some other background value. Here's how to directly construct a sparse array in Mathematica using a list of rules that specify where the non-zero elements are. You can see there are 10 non-zero elements in this 8x8 array. And here's a matrix plot of the resulting array. Sparse arrays are often useful in representing the structure of models of physical systems. Here's an example of solving the heat equation. The equilibrium temperature in a two-dimensional region satisfies this equation, where U is the temperature and Q is a heat source. If you discretize this equation, you get this difference equation, which you can see is actually a linear equation relating the temperature at each point I, j to the temperature of 4 of its neighbors. Since the temperature at each point is only related to 4 of its neighbors and not to any of the other points in our grid, this is a very sparse system of linear equations, and it's suitable for representation as a sparse array. Here we construct the system of linear equations corresponding to this discretized model. You can see it's a 900 by 900 system, but only 4,000 of the elements are non-zero. Here's a matrix plot of the overall structure of these equations. And we can quickly put together a test heat source by rasterizing the numeral 8. LinearSolve has specialized methods for solving sparse systems of equations, so the solution is very fast. And when we plot the result, what we are finding is the temperature distribution on a square plate heated by a heat source with a figure 8 shape. That's the end of our review of Mathematica's numerics functions. In this next section, we'll look at how you can control and customize the numerical algorithms that Mathematica uses. Each of Mathematica's numerics functions knows about many different algorithms. Normally, a suitable algorithm is chosen automatically based on the structure of the input. If you want to specify a particular method, you do so with a method option. In this example, we try out adaptive Monte Carlo integration on an integral whose exact solution is pi. In this example, we compare two different methods for solving a large, sparse system of equations. Using the timing function, we find that for this example, the iterative method is about 3 times faster. In this example, we choose the special method stiffness switching, which you can read about in the NDSolve Advanced documentation. This method regularly checks whether the system of equations appears to be stiff, that is, numerically unstable with normal methods. When this condition is detected, a temporary switch is made to a more robust method. This enables an accurate solution of this irregularly varying system of equations, without resorting to a very small step size. Just as Mathematica functions have options, most methods in Mathematica's numerics functions possess options of their own. These are specified in a list, where the method name is the first element of the list, and the remaining elements of the list are the options. One important special type of method option is a submethod option. In this AndIntegrate example, local adaptive is a higher level controller method, local adaptive subdivision, and the submethod is the particular quadrature rule to apply to each integration subregion. In this nminimize example, we use a method option to tell nminimize to start with 250 points in a random search for the global minimum of this difficult function. Advanced method options can also be used to access special methods. A good example is the event locator method of NDSolve. You can use this method to detect events during the solution of a differential equation. We'll use it to stop integrating at the moment our simulated projectile, such as a cannonball, lands on the ground. Here's a plot of our virtual firing range. This is the differential equation satisfied by a projectile moving under the influence of gravity and an aerodynamic drag force proportional to the square of the velocity. The initial condition for the projectile depends on the angle theta at which it was launched. When we invoke NDSolve on this system of differential equations, we use the event locator method. The event method option specifies which event we are checking for. In this case, the event is the intersection of the y-coordinate or height of our projectile with the height of our terrain at that point. We use the event action method option to tell NDSolve to stop integrating when the event is detected. Take a look at the result. Our cannonball goes about 45 meters. It's easy enough to put all of the above inside a manipulate statement. You can then explore finding the best initial conditions for firing the projectile as far as possible. It's very useful for debugging purposes to be able to monitor the numerical evaluations and steps taken by methods. One fast way to find out what almost any algorithm is doing is to use the evaluation monitor option. Set this option to an action that you want to take every time the operand of the numerical function is evaluated. In this case, we're observing the convergence of this method to the root of the equation. If you want to get a list of the points sampled or visited by a numerical method, then sow and reap are a good choice. Let's watch and integrate converge on the more rapidly varying region of this integrand, this region near x equals 0. At each evaluation, we sow the value of x. At the end, we reap the results and plot them. You can see the convergence of the adaptive method to the most rapidly varying region of the integrand near x equals 0. Whereas evaluation monitor catches each numerical evaluation of the operand, step monitor triggers at each step of the underlying method, which is usually less often. Step monitor is a good choice for getting a bird's eye view of functions like find minimum and NDSolve that operate in distinct steps. In this example, you can see the convergence of a two-dimensional minimization to the local minimum at x equals 1, y equals -1. One nice way to use step monitor is to monitor and visualize the solution obtained so far to a differential equation or other problem. In this example, we'll create a dynamic plot of the current solution of a differential equation stored in the variable sol. Initially, sol is empty, so the plot is blank. But in NDSolve, at each step, we will set sol to the current value of the solution. The result is a live plot showing the current state of the simulation as it proceeds. In this next section, I'll describe how approximate numbers work in Mathematica, including precision and accuracy. First, I'll talk about the difference between approximate numbers and exact numbers, and the different types of approximate numbers in Mathematica. Then I'll describe how the important options precision goal and accuracy goal work in Mathematica's numerics functions. There are three different levels of precision for numbers in Mathematica. First, there are representations for exact numbers. This includes integers, special constants like pi, and the values of special functions like square root of 2. Then there are arbitrary precision approximate numbers, with Mathematica's unique precision tracking. These represent numbers with some known degree of precision, such as 10 significant figures. The key advantage of these numbers is that their precision is automatically updated to reflect the effects of round-off error and other operations that can cause a decrease or increase in the number of correct significant figures in a number. Finally, there are fast machine precision numbers. These have the advantage of being directly supported by the hardware of most computers, leading to vastly greater speed. Their disadvantage is that there is no mechanism for tracking the effects of round-off error. By default, Mathematica uses machine precision numbers when you enter a decimal. When you apply mathematical operations to numbers with any of the three levels of precision, the precision of the output is determined based on the precision of the input. Typically, for exact input, you get exact output. A precision of infinity means an exact number. When the input is an arbitrary precision number, such as this number, which is shorthand for an 8 with a relative error of 10 to the minus 50, the result is another arbitrary precision number. The precision of the result is generally different from that of the input. In this case, the output precision is 50.3, which means a relative error of 10 to the minus 50.3. Note that the output precision is slightly higher than the input precision. This is because, for square root of 8, Mathematica determines that knowing the input to a relative error of 10 to the minus 50 is enough to be confident about the result with a relative error of just 10 to the minus 50.3. When the input is a machine precision number, the output is also a machine precision number. The special symbol machine precision is returned by the precision function in this case. When you combine numbers with different precisions, Mathematica determines the result to the best justifiable precision. In this case, adding the number 8, known with a relative error of 10 to the minus 50, to the number 2, known with a relative error of 10 to the minus 25, leads to the number 10, known with a relative error of 10 to the minus 25.7. Because machine precision numbers don't track round-off error, their precision is effectively considered to be lower than any other possible precision, even one significant figure. This means that if any part of a calculation is machine precision, such as this part, then the result will be machine precision as well. In Mathematica, precision refers to the relative error in an approximate number. This is effectively the number of significant figures. A different, equally valid way of measuring the error in a number is via the accuracy, which refers to the absolute error. This is effectively a measure of the number of correct digits known after the decimal point. A number with a given precision, or relative error, may have either a high or low accuracy, depending on whether the number is small or large. Here, a large number known to precision 10 is only known to accuracy 3. This is effectively because most of the known correct digits are to the left of the decimal point. Only 3 digits are known correct to the right of the decimal point. Here we have the opposite situation, in which a small number known to precision 10 is therefore known to a very high accuracy. This is because a relative error of 10 to the minus 10, taken relative to a small number, like 10 to the minus 7, implies an absolute error of just 10 to the minus 17. Most of Mathematica's numeric solvers can be given either a target precision to aim for, or a target accuracy, or both. If given both, the solvers will try to work until at least one of the two goals is satisfied. Here we ask and integrate to get a result with either relative error less than 10 to the minus 7, or absolute error less than 10 to the minus 2. And integrate effectively does whichever of these is easier. Which one is easier depends on whether the value of the solution is small or large. In this case, the accuracy goal was satisfied. If you set the accuracy goal to infinity, a numerics function will only return successfully if it is able to satisfy the precision goal. In this case, we obtained a result with 5 correct significant figures. One situation where you can't insist on getting a result with a certain relative error, or precision, is when the correct solution is 0. Relative to a value of 0, any error is infinitely large. So if the solution to your problem might be 0, then it makes sense to include an accuracy goal. In this example, the true exact solution is 0, and integrate obtains an approximate solution to within an absolute error of 10 to the minus 10, satisfying the accuracy goal. In this final section of the presentation, I'll give a few tips and techniques for programming with Mathematica's numerics functions and for optimizing performance. In practice, you often want to use the result of one numerical function as the input to another numerical function. In this example, we define a function sol of a that numerically solves a differential equation. The initial condition of the differential equation depends on the argument a of this function. And given a specific value of a, this function returns the solution in the form of an interpolating function. The most important thing to note about this function is that its definition is only meaningful when a has a specific numerical value, and not when a is an abstract symbol. You express this by attaching a condition to the definition of the function. This is often useful to avoid Mathematica emitting some warning messages later on. Once you've defined a function sol in this way, you can use it like any other function. Here's an animated plot of the solution to this differential equation as a ranges from 0 to 1. We can go ahead and ask more questions about the function sol of a. For example, we can compute the arc length of this solution as a function of a by using an appropriate numerical integration. Here's the function len of a that does that. Note that we once again express the condition that the parameter a should have a specific numerical value in order for this definition to be meaningful. If we plot the arc length as a function of the parameter a, you can see that there's a local minimum somewhere near a equals 0.8. And we can go ahead and use find minimum on our function len of a to find the precise location of that minimum. And in order to get this result, by now we've used a find minimum of an n integrate of an nd solve. When you have several layers of numerical functions calling each other, as we did in the previous example, you can eventually run up against issues of performance. A good solution is then to pre-compute intermediate functions as fast interpolating functions, and that's what we'll do in this example. So this example is related to the problem of deprojection in astronomy. When you look at an object on the sky, what you see is not the three-dimensional object, but a two-dimensional projection of that object. You see something like this, or like this, which is a smoothed plot of the same thing. But of course the real object is three-dimensional, and so the question is, given the two-dimensional projection, how can you find the overall three-dimensional structure? One common case is to assume that the object is roughly spherically symmetric. Then the density of the object as a function of r, the distance from the center of the object, is given by this well-known deprojection integral, where the function s is the surface density or surface brightness. That's what we are seeing in this plot. And in this example, I'm using this simplified model for the surface brightness as a function of radius. This function rho of r gives us the density as a function of radius, but you'll find that it's a relatively expensive function. It takes a few seconds just to plot it over the range of values r from 1 to 100. If we want to go ahead and use rho of r in some subsequent calculations, then it often makes sense to pre-compute rho of r over a range of values and interpolate the results. And that's what the function interpolation is for. The result is a fast interpolating function that takes the same values as rho of r, but is much faster. Compare the timing to produce the same plot that we produced above. Generally, if you give an exact input to a Mathematica function, you get an exact output whenever possible. Sometimes the exact output can be very expensive to compute or can take up a lot of memory. For example, suppose we nest this function f twice, or we nest it 4 times. The more times we nest f, the more time and memory is required to create and store the resulting exact number. If you want to get a machine precision representation of this number, 2 apparently equivalent ways are to either use the n function to obtain a machine precision representation, or to nest f using the approximate number 5.0 as the initial value instead of the exact number 5. We get the same result. In some cases, you may need the exact expression. For example, here we use the second argument of n to obtain 50 verified correct digits of the same number. Or you may wish to perform a symbolic operation, such as differentiating this nested function with respect to x. However, if you only need the final approximate number, then you're usually better off using approximate numbers from the beginning. Here's an example where we nest f 20 times. You should imagine how large this expression would be if we used the argument 20 to nest here. This calculation takes more than a second to perform, because before numericizing the result to give our machine precision number, Mathematica first constructs this very large exact expression. If we instead begin with the approximate number 5 in machine precision, then no large exact expression of this form is ever created, and the computation is essentially instant. When you work with lists or arrays of machine precision numbers, including real numbers, complex numbers, or machine integers, Mathematica may store these internally in a special format known as a packed array. Packed arrays are created automatically by Mathematica, and normally you never need to know whether they are being used. However, here's an example where a packed array is used by Mathematica. This is a list of 10 million random real numbers. You can use an internal function in the developer context to obtain the same list in an unpacked format. For all intents and purposes, these two lists are exactly equivalent to each other. However, because of their different internal representation, packed arrays use less memory than unpacked arrays, about 4 times less memory in this case, and fundamental operations on them are faster. Since operations on packed arrays are much faster, when you're writing performance-intensive code, you may want to ensure that Mathematica is able to keep all of your large arrays packed at all times. Here's an array of 1 million random real numbers. Mathematica will store this as a packed array. We can temporarily switch on some extra messages related to packed arrays. This can be useful when tuning your code. Any exact quantity, such as this exact 0, causes the machine precision array V to be unpacked into a regular Mathematica array. Since we've turned on these extra messages, we get a warning about this fact. If we perform some fundamental operation on the array V, such as exp of V, then the result is computed relatively slowly. If we replace this changed element of V with a machine precision 0, then Mathematica is able to repack the array, and fundamental operations, such as exp, become much faster. Finally, let's switch these messages back off. The important thing to remember about packed arrays is that every element in your array needs to be a machine precision real or complex number or a machine integer. Any exact quantity, such as an exact zero, or any integer or rational number, or variables such as x and y, will cause the array to be unpacked into Mathematica's normal array format. The compile function converts Mathematica code into an optimized virtual machine language for faster execution. As of Mathematica 8, compile can also produce a C representation of your code, compile the C code into a dynamic library, and immediately load that library into Mathematica. This lets you produce optimized functions that are not significantly slower than Mathematica's own fast built-in functions. Here's an example of a function that computes how close a point C is to the famous Mandelbrot set. Using input form, we can look inside at some of the details of the function f. You can see the virtual machine instructions and the compiled dynamic library that was created on your computer. This compiled function is fast enough to visualize immediately for a range of values of C. Here we zoom in on a smaller piece of the same plot. Note here that we apply f to a two-dimensional array of values of C. This is possible because compile is able to produce listable functions, just like Mathematica's built-in fundamental operations such as sine and cos and plus are listable. In practice, you rarely need to invoke the compiler yourself because Mathematica does it automatically in many places. In all three of these examples, Mathematica compiles the function that appears in the first argument. It can pay to be aware of situations where you can inadvertently prevent Mathematica from performing this automatic compilation. Automatic compilation relies on Mathematica being able to symbolically evaluate your function or expression. If you define a function that only evaluates for specific numerical values, such as this one, then Mathematica can't apply automatic compilation. In this case, it may be worthwhile to manually compile the function yourself. Here we create a compiled version of this expression, and then define g of x just as for f of x. The result is much faster. Thanks for attending this presentation, and I hope you learned some new techniques for working with Mathematica's numerics functions.